Friends, welcome to the lecture 55, where we are going to do an example problem for lateral torsional buckling. Okay. We will take a simply supported beam for a span of 5.7 meters subjected to two kinds of loads. One load is your dead load, which is about 9.58 kilonewton per meter, and over and above we have an imposed load which is uniform distributed, and this is imposed load, otherwise called as live load, of intensity 6.25 kilonewton per meter. We will call this end as A, this end as B. Okay. Now, we are going to use a specific kind of trial beam section. The beam section what we chose is UK beam 356 by 171 by 51, which is S 275 grade. Okay. So, for the benefit of the users, let us show the cross section of the beam. This is what the cross section of the UK beam 356, 171 and 51. Based on this, let us write down certain dimensions. Now, the first step is to estimate the maximum bending moment. We call this as MED. Let us see what are the factored loads. W, which is going to be 1.35 into 9.58, okay, this value, plus 1.5 into 6.25. So, I am using a different factor for live load and dead load, okay, which is going to be 22.31 kilonewton per meter. So, I can quickly find out MED as WL square by 8 because it is simply supported section. So, it is going to be 22.31 into 5.7 square by 8, which will give me 90.6 kilonewton meter. This is my demand. Okay. Now, for the section shown on the screen, the properties are like this. H is 355, that is why the section is called 356, okay, 355. B, which you see here, is 171.5, these are all millimeters, friends. TW, which you see here, thickness of the web is 7.4 millimeter. TF, thickness of the flange, which you see here, is 11.5 millimeters. R is 10.2 millimeter, which is actually the radius of curvature being used for fabricating the ends of this rolled steel section. Okay. These are available in the standard tables, they are referred as UK steel sections. Similar are also available in Indian code. Okay. We have Indian code SP 61, which will give you the section properties and so. So, the steel grade which is being used is S 275, which means sigma y is 275. Okay, yield strength is 275 Newton per mm square. We will use Fy because that is the symbol used in Eurocode. Okay, let us check quickly what is the maximum thickness which is permitted for this kind of steel. The maximum thickness in the section available is 11.5. This is lesser than 40. Okay, that is a check. Okay, that is a check. So, this is according to, I will write here, this is according to EN 1993 1 1 2005 table 3.1, that is what I have used. Okay. Now, let us come to section classification. Section classification depends on square root of 235 by Fy, which comes to 0.92. Okay. This is as per table 5.2. I am using the same code. Let us talk about the outstanding flange. The outstanding flange, which is under uniform compression, we will work out the C value is B minus TW minus 2R by 2, which will be B is 171.5, thickness of the web is 7.4 minus 2 times of 10.2, that is the radius given, okay, divided by 2, which gives me 71.85 millimeters. So, a factor C by TF is 71.85 by 11.5, which is 6.25, which is less than 9 epsilon. So, this gives me that it is class 1 element. This is as per table 5.2 of the code. Okay, so, it is a class 1 element now. Let us talk about the internal compression member. Okay. So, now we are considering web in bending. Bending can also have compression, bending compression. Let us compute that for C is equal to H minus 2TF minus 2R, which is going to be 355 minus 2 times of 11.5 minus 2 times of 10.2, which gives me 311.6 millimeters. Now, C by TW, which is 311.6 divided by 7.4 is 42.1, which is less than 72 epsilon, which also guarantees and classifies as class 1 element. This is as per table 5.2. Okay. Having said this, we are now using, so now the section used for trial is class 1 section. Okay. We have clarified that. Now, let us do the second step, which is to compute the moment of resistance, which is MBRD. Okay. We will use class 6.2.4 of Eurocode 1993-11 2005. According to this, MBRD is given by WPLY into Fy by gamma m naught. So, we will say 896, that is capital W, 275 is my yield strength, and gamma m naught is taken as 1.0 to 10 power minus 6. So many kilonewton meter, which gives me 246.4 kilonewton meter. Now, friends, please note the capacity, which is moment of resistance, is higher than the demand, which is M, what we have used the symbol there, MED. Okay. So, one can say, so since that is 246.4 is greater than 90.6 kilonewton meter, we can say the section is safe against bending. Okay, we have checked it. We are now checking a trial section. Now, let us check against LTB. So, to check against LTB, we are going to check the elastic critical moment. Now, to compute the elastic. So, based on the support conditions, and the loading applied at the top flange level. So, now support conditions, we should say simply supported. Load application, top flange. We can calculate MCR. We already derived this equation. MCR is given by, that is 3 parameter formula, C1 pi square EIZ by KZL the whole square of Kz by Kw the whole square IW Iz plus KZL the whole square G I tau pi square E I Z plus C2 Zg minus C3 Zj square raised to the power 0.5 minus C2 Zg minus C3 Zj. This equation only we wrote the previous lecture, please refer back. So, now we have to use the figures and tables. So, the conditions are the beam is simply supported, therefore, the effective length factor which is Kw, which is also equal to Kz, which is 1.0. Now, since the load is applied on top flange, Zg will reduce the section by half. So, what does it mean? Zg will be actually h by 2, which is 355 by 2, which is 177.5 millimeters. C1 from table, which we already said is 1.12, C2 from table is 0.45, then from the table we will also know Iz for the section, which is 968 centimeter power 4, Iw is 0.286 dm to the power 6. This is given in UK steel tables. Okay, I am just taking the value directly from there. So, 1 decimeter is 10 centimeter. Let us have this correction here. I tau is 23.8 centimeter 4 and E of course is 2.1 10 power 5 Newton per meter square, and G is 77 kilonewton per mm square. Okay. Now, we know all the values. See here, we wanted to know, I am just checking, we wanted to know C1, we have E, we have, okay, Iz, we have Kz, we have L, of course we have, okay, Iw, we have Iz, we have G, we have I tau, we have Z, Zg, C2, we have Zg, we have. So, we can compute these values directly and I will get MCR as 121.9 kilonewton meter. Okay. So, the next step is to estimate the buckling factor, which is psi LT. This depends on slenderness. So, slenderness parameter, which is lambda bar LT, is given by square root of Wy Fy by MCR. We already have this value. See here, Wy we have, okay, Fy we have, now MCR also we have. So, let us substitute them. It is going to be square root of 896 into 10 power 3 into 275 divided by 121.9 10 power 6. I get this value as 1.423. You can please check this. So, now we consider this section as hot rolled. So, we will use the special case method. There are two methods by which we can do. Okay. So, we know from the table for H by B, which is equal to 355 by 171.5, which is 2.05 greater than 2, we should use buckling curve C. Am I right? We have seen this in the last lecture. For rolled section, for H by B more than 2, what buckling curve we should use a special case method. Please refer back to your notes. Now, from the buckling curve for curve C, we can directly find alpha LT as 0.49. Okay. Then we can compute phi LT, which is given by 0.5 times of 1 plus alpha LT times of lambda bar LT minus lambda bar LT 0 plus beta lambda bar square of LT. So, let us work out phi LT in this case 0.5 times of 1 plus 0.49 1.423 minus 0.4 plus 0.75 1.423 square, okay, which gives me 1.510. So, now I can say psi LT is given by 1 by phi LT plus square phi square LT minus beta lambda square LT, and which should be the minimum of 1.0 and 1 by lambda square LT. Okay. So, now I get psi LT as 1 by 1.51 plus square of 1.51 square minus 0.75, that is the beta value, into 1.423 square, okay, which comes to 0.42, which is less than 1. And also 1 by lambda bar square LT is 1 by 1.423 square, which is 0.493, right. So, the value what we got is 0.42. So, I can now say psi LT can be taken as 0.4. It satisfies both the conditions, no. Okay. Now, we have the beam under uniform distributed load. So, for this load distribution, or specifically for this bending moment distribution, from the table which we discussed in the last lecture, I can find Kc as 0.94. Please see the table. Now, I want to calculate the F factor, because I am using the second method. So, F factor is required. F is given by 1 minus 0.5 times of 1 minus Kc of 1 minus twice of lambda bar LT minus 0.8 square should be less than or equal to 1. Let us check. 1 minus 0.5 times of 1 minus 0.94 of 1 minus twice of 1.423 minus 0.8 the whole square, we get this value as 0.993, which is less than 1. Okay. So, F factor is now computed. Therefore, we can then find the MOR, which is actually MB of RD. MB of RD is given by psi LT by F WPL Y Fy by gamma M1. We will substitute 0.42, that is psi LT, is it not? 0.42, F factor is 0.993 and WP is 896 10 power 3 into 275 by 1. We already said gamma m is 1 for this kind of distribution. Okay. So, this value comes to be 104.2 kilonewton meter. Okay. So, now the demand is MED, which is 90.6 kilonewton meter. The capacity MBRD, which is 104.2 kilonewton meter. Since the demand is lesser than the capacity, the beam is safe against lateral torsional buckling. So, we are just checking whether the beam is safe. So, what is the comment here? No additional lateral restraints are required. Otherwise, you have got to provide lateral restraints, as we discussed in the previous lectures. Let us solve the same problem using IS code. We are using IS 800 2007, that is the steel design code. We are checking the section. So, we will take the section as ISMB 400 at 61.6 kg per meter. So, let us say the beam is simply supported over a span of 8 meters. Okay. The total moment under uniform distributed load is 50 kilonewton meter. FY 250 grade is to be used. Okay. So, check the beam for lateral torsional buckling. That is the question asked. Okay. Let us do that. Let us first see the section properties. Area of the cross section, which is 78.46 centimeter square, which is 7846 millimeter square. Depth of the section, H 400 mm. Thickness of the flange 16 mm. Breadth of the flange 140 mm. Thickness of the web 8.9 mm. This can be seen from steel tables. Okay. Moment of inertia about the minor axis, also given in the table, which is 622.1 centimeter 4, which is 622.1 10 power 4 mm. IXX, which is about the major axis, which is 20458.4, which is 20458.4 into 10 power 4 mm4. Then we will do the section classification. The first step is section properties. We know Fy is 250 Newton per mm square. Okay. Let us look into table 2 of IS 800 2007. So, epsilon is given by square root of 250 by Fy, which is equal to 1, and B by Tf in our case is going to be overhang. So, 140 by 2 divided by 16 which is 4.375 less than 9.4 epsilon for epsilon equal to 1, okay, and d by TW, which is 400 minus 2 into 16 divided by 8.9, which is 41.35, which is less than 85 epsilon, okay. So, friends, in this equation, if you note, this B actually is Bf by 2. Look at figure 2 of IS 800. Okay. And of course, D is dW, only the web. Okay. So, now based on these data, we can classify the section as, okay, classified as plastic section. Okay. Furthermore, H by Bf is 400 by 140, which is 2.86 greater than 1.2, and Tf is 16 mm less than 40 mm. So, from table 10 of the code, buckling class about x axis is A and buckling class about y axis is B. So, then the next step is to find out MCR, that is elastic lateral buckling moment. Okay. Now, the section is symmetric, it is prismatic, and it is simply supported, okay, because we should have the bending moment distribution also. These are the conditions. For these conditions, MCR is given by square root of pi square EIY by L LT square of GI tau plus pi square EIW by LLT square. Okay. This is as per class 8.2.2, 2.21, sorry. So, in this, let us substitute the values. E is 2.1 10 power 5. So, we have E, okay. Mu is 0.3, therefore, G is E by twice of 1 plus mu, which gives me 2.1 10 power 5 by twice of 1 plus 0.3. I get this value as 80.77 10 power 3. Okay. So, I have G. IY already we have. Let us see what is IY, 622.1. So, IY we have 622.1 10 power 4. Effective length, which is LLT, is 1 point L, which is 8 meters. So, this is according to table 15. class 8.3 for torsional fully restrained but warping not restrained in both the flanges. For this condition, we have taken this effective length. Okay. So, I tau torsional constant which is summation of bi TIQ by 3. This is for open sections. So, let us find out for our problem I tau twice of 140 into 16 cube by 3 plus 368 into 8.9 cube by 3, okay, which comes to be 468.77 10 power 3 mm4. Warping constant. So, let us say I tau we have, LLT we have, we want to find IW. So, warping constant IW is 1 minus beta f Iy Hy square. This is for I sections. So, now what is beta f? Beta f is IFC by IFC plus IFT, where IFC and IFT are moment of inertia of tension and compression flanges about the minor axis of the section. Okay. Let us compute IFC, that is very easy. So, IFC about minor axis. So, B T cube by 12, I can now say this is going to be 3.66 10 power 6 mm4. So, we have the same as IFT, tension and compression flanges minor axis moment of inertia is same. Okay. Having said this, let us now find what is Hy, which is actually the distance between the shear center of two flanges of the cross section. So, Hy in my problem will be H minus Tf by 2 into 2. Which will be 400 minus 16, which is 384 mm. Beta f, which is IFC by IFC plus IFT, which is 3.66 10 power 6 by 3.66 10 power 6 into 2, which is 0.5. Now, let us work out IW, which is given by 1 minus beta f Iy Hy square. Let us substitute them. 1 minus 0.5 Iy 622.1, that is here, 622.1 10 power 4, Hy is here 384 square, which gives me this value as 2.293 into 10 power 11 mm6. Okay. Now I can find MCR. MCR, let us copy this equation of MCR back again. Is given by this equation. Okay. Let us substitute, which will be equal to square root of pi square 2.1 10 power 5, that is my E value. I is 622.1 10 power 4. This is 8000 square. Okay. I am doing it in millimeters and newtons. Okay. Then 80.77 10 power. That is my G value. See here. Okay, that is my G value. I tau is 468.77 10 power 3. That is my tau value. Okay. Plus pi square 2.1 10 power 5. I warping constant, we already have it here, 2.293. Okay, divided by 8000 square. Okay, so I get MCR as 95.51 into 10 power 6 Newton mm, which will become 95.51 kilonewton meter. Okay. Now let us compute the design bending moment. The design bending moment is MD, which is beta B ZP FBD. This is as per class 8.2.2 of IS 800. So, what is beta B, which is 1 for plastic sections? We already declared this is a plastic section. What is ZP? Is the plastic section modulus. And FBD is the design compressive bending stress. Which is actually equal to psi LT Fy by gamma m naught. So, let us say what is psi LT? We already know this. Phi LT plus phi LT square minus lambda square LT. Okay. Phi LT is 0.5 times of 1 plus alpha LT into psi LT minus 0.2 plus alpha bar LT square. Alpha LT is the imperfection factor, which is 0.21 for rolled sections given in the code. Let us calculate lambda LT, which is actually equal to square root of beta B ZP Fy by MCR, which is less than or equal to square root of 1.2 ZE Fy by MCR. So, let us say what is ZP? 1176163.26. This is for ISMB 400. ZCE is 1022.9 10 power 3 mm cube. Okay. We can refer these values from SP61 steel tables. So, now alpha lambda LT will be 1 into 1176163.26 into 250 by 95.51 10 power 6, which will become, which should be less than or equal to 1.2 times of 1022.9 10 power 3 of 250 by 95.51 10 power 6. So, now we get this value as 1.79 less than or equal to 1. This is 7579. So, it is okay. Okay. Once I have this value, can substitute back in phi LT and cut phi LT. Let us do that. So, therefore, phi LT is going to be 0.5 times of 1 plus LT minus 0.2 plus lambda bar square LT, which will be 0.5 1 plus 0.21, that is what my alpha LT is, okay, 0.21 into 1.75 minus 0.2 plus 1.75 square, okay, which comes to 2.194. So, now can calculate this value as 1 by phi LT plus phi LT square minus lambda square, which will be 1 by 2.194 plus 2.194 square minus 1.75 square, which comes to 0.284. Okay. Now, FBD, bending stress in compression, is LT Fy by gamma m naught. Now, gamma m naught is equal to 1.1, which is the partial safety factor of member to resist buckling. So, let us substitute that, which will become 0.284 into 250 by 1.1, which comes 64.616. Okay. So, now the design bending strength is governed by the lateral torsional buckling, so MD is beta B, ZP, FBD, which is 1.01176,163.26 into 64.616, which is 75.99 or 76 kilonewton meter. Okay. The applied moment is 50 kilonewton meter. The capacity is 76 kilonewton meter. Therefore, we can say the beam is safe against lateral torsional buckling. No additional restraints are required. Okay. So, friends, in this lecture we learned two examples of checking the design for lateral torsional buckling. One we did with Eurocode, second one we did with Indian code. In both the cases, since the capacity of the section is larger than the demand of the section, so we declare they are safe against LTB. So, the procedure is very straightforward. It is well illustrated in both the codes. Equations and supporting tables are available to you. So, only you got to practice more number of problems. So, take some sample sections, work it out and see whether the chosen section is safe against lateral torsional buckling. Okay. Thank you very much and have a good day.